Modern drug discovery and material science share a severe bottleneck. The algorithms driving these fields do not recognize physical geometry. You can feed a computer a chemical drawing or point it to a 3D ball and stick model, but it cannot process those structures natively. To solve this, researchers use molecular graph theory. This framework represents a molecule as G equals V, E, converting physical structures into computable matrices. The V stands for vertices, mapping to atoms. The E stands for edges, mapping to chemical bonds. Converting chemistry into discrete graphs lets machine learning models systematically compare and learn from molecular architecture. Before building any matrices, computational chemists define the resolution of their graph. They determine exactly how much chemical detail the algorithm requires to execute its task. The primary variable is the treatment of hydrogen. In an explicit hydrogen graph, every hydrogen atom is a distinct vertex. This high-resolution model preserves total geometry, necessary for calculating stereochemistry. By contrast, a hydrogen-suppressed graph omits hydrogens as separate nodes, storing them as hidden labels. This reduction offers critical computational efficiency for massive datasets. This choice of resolution determines both the chemical accuracy of the model and the computational cost required to run the neural network. Once the resolution is set, the visual graph is converted into a table of numbers that the algorithm can process. Topology is mapped using an adjacency matrix, denoted A. It records connectivity, assigning 1 where a bond exists and 0 where not. Because standard covalent bonds are undirected, the matrix is symmetric. If carbon 1 bonds to carbon 2 bonds to carbon 1. Local neighborhoods are quantified by the degree matrix, or D. This counts the total number of bonded neighbors for each specific atom and places those integers strictly along the matrix diagonal. The adjacency matrix defines the raw molecular skeleton, while the degree matrix defines local node density. Combined, these matrices allow us to track how information flows through the structure. In a molecule, an atom's behavior is dictated by the environment pulling on it. This is captured by the graph Laplacian, L. Using L equals D minus A, the matrix measures exactly how different each node is from its neighbors. It provides the foundation for structural diffusion, balancing an isolated state against neighbor pull. The Laplacian also verifies the graph's integrity. The number of zero eigenvalues in the Laplacian perfectly equals the number of connected components in the graph. A connected molecule yields exactly one zero eigenvalue. This diagnostic allows algorithms to verify contiguous molecular structure instantly. When scaling these matrices to massive molecules or crystal lattices, researchers face a memory limitation. Standard n by n matrices become too large to store. Because most atoms in a large system are only bonded to a few neighbors, the adjacency matrix is filled almost entirely with zeros. Storing these non-existent bonds wastes significant memory. Graph neural network libraries bypass the full matrix by compressing data into a COO format called the edge index. This stores only the specific coordinate pairs where an active connection exists. These sparse tensor representations enable functional, high-performance molecular machine learning at scale. These matrices enable message passing, the mechanism where each atom updates its identity by mixing in information from its environment. In a neighbor mean update, we multiply the feature vector by the adjacency matrix, aggregating the values of every bonded neighbor. To prevent values from scaling out of control, we apply normalization. Multiplying by the inverse degree divides the accumulated value, producing a smoothed average. Over successive layers, message passing smooths features across the topology. This allows the model to learn that a generic carbon atom is chemically contextualized by its neighboring alcohol group. Standard topological graphs do not account for 3D coordinates or stereochemistry. They track connections but remain unaware of spatial orientation. To reflect physical reality, algorithms use radial basis functions. These convert a single distance measurement into a soft histogram of vector activations, providing a smooth pattern for the model to learn from. Because distance alone cannot resolve bond angles, models use spherical harmonics. These encode the exact 3D angular orientation of atoms along the x, y, and z axes. Modern networks treat the computational edge as a densely packed data structure. It stacks binary topology, bond weights, distance encodings, and directional vectors into a single multi-dimensional unit. Molecular graph theory translates the continuous reality of chemistry into a mathematical network. By providing a framework to parse chemical structure, it allows algorithms to predict physical properties, reason through geometry, and design the materials of the future.